Hello, welcome to video 9 in Advanced Mathematic Modeling. I just realized for some reason the recording stopped in the end of my last video, so just let me finish the explanation. So we were discussing here Benford's law, and so what was the distribution of the first digit in a sequence of random numbers from a data set. And so we had this distribution that the first digits appear quite more often. And in order to see who would win this bet here, if the digit is between the first 4 or the remaining 5 alternatives, we can plot the cumulative distribution. The cumulative distribution starts by 0.3 and then monotonically increases until 1. So that's the cumulative distribution for this PDF. So again, you see the difference between the probability density and the cumulative density. And now the question, what is the cumulative distribution at 4, meaning the digit is between 1 and 4, and this is 0.7. So we have a 70% chance to have a digit between 1 and 4, and only 30% chance to want it to be one in the remaining digit. So you would have lost the bet against me. So now what's the reason for this distribution? Why are the small digits appear so often? That's a non-trivial thing, and to calculate this distribution, it's really a bit sophisticated. But to give an intuitive idea, at least that's my understanding why the first digits appear more often. So let's just write down numbers here. 1, 2, 3, 4, 9, and then 10, 11. And let's see, if you just would write down the first 20 numbers and then stop, then you see the digit 1 appeared quite more often than the other digits. And if we would continue now, then we would have a lot of 20s, then the digit 2 would also appear quite often. So if we have a finite range of numbers where we take the first digits, somehow it's clear that smaller digits have a higher chance to appear more often, because they're the first to appear if we increase the numbers. But that's just an intuitive explanation. In order to come from this to the real distribution, that's beyond what we want to do in this lecture. Maybe some historic anecdote. So this law was discovered by Mr. Newcomb in 1881. And in fact, this was discovered in such table of logarithms. And so Newcomb found that if he had such a book of this table of logarithms, the pages were used differently. Some pages still looked very new, and some pages were used quite often. And this then he saw that numbers which have a small digit were looked up much more often than others, and so that's how it was found. But then, funny again, this was forgotten, this knowledge, and discovered again maybe 50 years later by Frank Benford, and now it's this law is called Benford's law or Benford distribution. And that's a common case in science, that things are forgotten and then later rediscovered, and that's famously quoted by the Stigler's law. No law is named after the person who discovered it. Here, so that's something that we see quite often. So that was the remainder of this video from last time, which was lost. Somehow the recording stopped, and now what do we want to do now? We have seen now quite a number of such distributions here, Benford's and other distributions. So what are ways to characterize such a distribution? So this brings us to a new topic, expectation values and moments, so which allow us to quantify a distribution. So what is the expectation value? And this is really the fundamental procedure how to extract information from a distribution. So what do we need? So first we need the distribution. P of x, and we need just an arbitrary function, f of x. And then we can calculate the expectation value of this function f of x with respect to the distribution. Sometimes we write e for expectation value, but more often we use this brackets here, so we have the expectation value of the function f. And this is just defined as an integral over our probability distribution, integrated over the random numbers dx, but weighted with the function. And the borders here go over the interval of the distribution, either from -infinity to +infinity, or the range where the random numbers are defined. So that's the fundamental quantity. If we have a discrete distribution, then the expectation value f of x is then just, instead of an integral, given by a weighted sum. We take the f of xi and the pi, and we sum over all order I. Okay, so what can we do with this expectation value? I mean, first we can see some properties. The expectation value is linear. So if we have the expectation of a plus b, this equals the expectation of a plus the expectation of b, and the expectation of constant c times the function f of x is c times the expectation of the function f of x. There, so we can we just have the linear properties because we just have here an integral. Okay, now let's take an example. What is the expectation of a constant? Let's first take the expectation value of 1. What is the expectation value of 1? That's the integral of 1 times p of x dx. And since our probability distribution is normalized, this is just 1. And by the linear property, the expectation value of a constant is just the constant. So that's not so interesting. So let's take as another example, what is the expectation value of the identity function? Let's take the expectation value of x. So what is this? That's the integral x p of x dx. And this is the fundamental, also the first dominant property of a distribution, the expectation value of the random number itself. And sometimes we call these also just the expectation of the distribution, the mean value. Or just the expectation. So often if we just say we take the expectation of a distribution, we mean we take the expectation value with the function f of x equals x. Okay. But in general, expectation always needs to specify a function. Yeah. And now so we have done this. So what can we also do? We can calculate moments of a distribution, the nth moment. What is this? That's just the expectation value of the variable x to power n. So in this integral, x to power n p of x dx. And you see the mean value is just the first moment. And when we calculate all the moments, we have the information of all the moments. Basically, this means it's the same information as that is contained in the whole probability distributions. So the moments allow to characterize the distribution. And important or most important are the first and the second moment. Now, the second moment itself is not so interesting per se, but what we can do, we can define the variance of our distribution, which we sometimes denote sigma squared. And so what we take the expectation of the difference of a random variable from its mean value. So we take the difference x minus the mean value. But now, since these deviations from the mean can be positive or negative, so we square this so that every deviation makes a contribution. And then we take the expectation values from this. Now when you work this out, when you use here the laws of linear properties, and so you factor out here this square of the sum, so you will see we can write this also as the expectation of the second moment minus the square of the first moment. Yeah. So now if you want to see what's the difference if you first square a random number and take the expectation, or take first the expectation and then square, this difference is just the variance. So the variance itself is has still all the squares in order to get to units of the random variable itself. We need to take the square root again, and then we come to the standard deviation of a random variable x sigma, and this is the square root of the variance of x, the standard deviation. And I do this very fast here because I think that most of you have seen all this expectation values, variable and standard deviation, so I don't have to make this too much detail. So maybe let's do a sketch. Let's say here we have our distribution of our random number. And then, so maybe I should have done this already here. So when I calculate the mean, so the mean typically is will be somewhere in the center of the distribution. So this will be here the mean value, where it gives you the typical average of your distribution. And now when we want to know something about the width of the distribution, and then the standard deviation describes you the width of the distribution. And in fact, if you would calculate this for the Gaussian distribution that I showed you before, and this parameter sigma is exactly the standard deviation of the Gaussian, and here in these examples the mean and standard deviation were 0. So you see what we want to do. So let's say we know the distribution is characterized by a function. So we need infinite many information to have all this distribution, and I want now to nail down all the information content in this probability distribution by a few numbers. So what's the main properties? And that's given by, and these properties I get by expectation values. The first is the mean, so what's the typical random number that I could expect? And the second is the standard deviation, so that's the width of the distribution. And in order to get the standard deviation, I need the second moment. Now in a similar way, we could continue and create higher moments. And in fact, you can prove that if we know all of these moments, we have this information, then we can recover our whole distribution. Maybe I should say already now, there is no guarantee that these expectations exist. We have to integrate over probability distribution, and this expectation could diverge. Yeah? And in fact, for the most interesting distributions we discover later in the lecture, many expectations will diverge. So it means it's not so easy to characterize the typical value of a random number. For example, when we say the mean value gives the typical number that we find, this holds only for well-behaved distributions. But if we have heavy tail distribution, the mean number does not give you the typical outcome, and the mean number might not even be defined. So this distribution might not even have a mean number. So take this here with some caution that these moments might not be defined, yeah? Particularly when we later have power law distributions. But basically, when we have all moments, if they exist, then all the moments we can reconstruct our distribution. So now if we go to higher moments, so what are the most important higher moments? So let's say if we go to the third moment, we get the skewness. So the skewness is defined also as an expectation value, and now we take the difference of the random number from the mean, we normalize by the standard deviation and take the third exponent here, and the skewness gives us some information about the asymmetry. The asymmetry of the distribution. So I mean, if you have a Gaussian that's nicely symmetric, but you could also have a distribution which is skewed, so it would be maybe something like this. Yeah. In Germany, it's the Schiefe. Something, if you want to go to the fourth order, that's the kurtosis. So it's the skewness, kurtosis, kappa, This is an expectation, and now we take the difference from the mean normalized by the standard deviation to the 4th power, and the kurtosis tells us something about the heaviness of the tail. So let's say we take as reference again Gaussian P of x, and now if we have a distribution which has a longer tail, so then we have some kurtosis. We can characterize this by the kurtosis, but in practice, in this lecture, we will always we will only deal with the first moments. That will be enough, and we don't bother with higher moments like skewness or kurtosis. But then also, just for completeness, we probably know that the expectation values are not the only way to characterize a distribution. So instead of calculating the mean, we can also take other ideas to calculate the center of the distribution. And one important thing would be the median. Median value. And here the idea is, let's say we have our distribution P of x, which is centered here, and then we will say, yeah, the mean should be somewhere here. And so how can we systematically find this? Okay, so we take the cumulative distribution, which increases from 0 to 1. Let's see how this cumulative distribution approaches 1. And then we say, okay, we now take the value where the cumulative distribution has just reached the middle, and say this value is the median. It's x1/2. It's often called that. So that would be then the median of the distribution. And sometimes this is a more robust quantifier in order to know the typical value that you have in the distribution than the mean value. So this goes all then if you go later to really parameter estimation and really trying from data to really nicely characterize the distribution. But for our purposes, we want to calculate properties of distributions, and in all of these things where we calculate stuff, that's done with the expectation values mean in first moment. So maybe let's explore this in a small example. We take the uniform, continuous uniform distribution in the interval between 0 and 1. So we know that we can write this probability distribution as 1, because then it's normalized, the integral over this rectangle is 1. So what is the expectation or the mean value of the distribution? And this is just simple, straightforward integration. So we have to integrate x times p of x dx. In this simple example, this p of x is just 1, so we just have to take the integral between 0 of 1 of x dx. And so you see this is 1/2 x squared. And the borders between 0 and 1, and this is 1/2. And so we see the expectation is, as we would have guessed, exactly in the middle of this distribution. So the mean value is 1/2. So, but now what's the standard deviation? Maybe you, if you don't know this, stop the video and think, what would be your intuitive feeling what the standard deviation of this is, and then calculate the standard deviation and then compare now to the calculation I'm doing in the following. So I assume you have done this calculation, and now let's see compared to mine. So first I calculate the second moment. So now I have to integrate x squared in this range. This is 1 over 3 x to power 3 between 0 and 1, and this is 1 over 3. And now we calculate the variance. So this is 1 over 3, that's the second moment, minus the first moment squared, so minus 1 over 4, and this is 1 over 12. And then we calculate the standard deviation. It's just the square root of this 1 over square root of 12. So it's 1 over 2 square root of 3, and this is 0.28. So you see the standard deviation is not going to the middle. This would be 0.25. Yeah. It's a little bit more. And this would be the typical range around the mean value that you have here in this distribution. Okay, so now we have covered some basic example of distribution, and we have seen how to characterize them with moments and expectation values. Thank you.